we have our wave equations. Now let's look at the solution we're going to use most in optics, and that is the solution is an electromagnetic plane wave. And what we mean by that in words is simply a one-dimensional traveling wave. And just like the string, that means it's a function of x minus vt, or in this case, x minus ct, because we know that all light waves go at the speed of light. So if you think back to the string, we had the normal mode solutions. We had those traveling wave solutions that were easy to make. You just put x minus vt. This is just a traveling wave solution. And this is what we do almost all of optics with, is plane waves. So we're going to spend a lot of time obsessing with exactly what a plane wave is. So let's start with a mathematically simple one. So let's look at one. Let's look at a plane wave moving along, I think z-axis with the E field along the x-axis, and let's ignore the B field. That's easiest, is just to pretend the B field isn't there. We'll get back to it. We'll talk about it in a little bit. So we're going to write it that way. What we could do is say, okay, the E field. And I'm talking about the E field for all of space and time. Okay? When I say it's one-dimensional, we're not going to just write it in one dimension. I'm just saying it only moves along one dimension. It's not really a one-dimensional thing. So the E field for all of space and time for this plane wave is equal to E naught. So that's sort of that's the size of the vector, the cosine, and K is the spatial oscillation part. It's moving along the Z, so it's kz minus omega t, because we know that's the form of kx minus vt. And that's in the I hat direction because we said it's along the x-axis. All right. And then we'll point out that it has no component along the j-axis and no component along y, no component along x. So that's how you would write the plane wave. So it's called a plane wave because the E field is constant on a plane. So the place where the E field is constant is called a phase front. It's the place where the E field is constant would be where this phase is constant, right? Because if you have some space and time situation where this is all the same, then all over that plane it's just going to be E times I. Or if this whole thing is always 0.5, it'd be half of E times I. So let me show you an illustration of what that will look like, so we can really get the picture of a plane wave into our heads. Let's see. So here we go. So here is our x, y, and z axes, and here I've drawn a plane. And we said that the E field was along the x direction, so a minute we'll draw E this way, and we said it's going to move in the z direction. So if I start letting the thing move, this plane moves forward, and here we're mapping out the E field vectors. And remember, it was a cosine, and I accidentally drew a sine. My most humble apologies. But here it is, a sinusoidally varying E field magnitude in the x direction, no component in the y direction, and no component in the z direction. And if you stop at one point along the sine, everywhere in this plane has the same E field as the one right here on the z-axis, right? And then it can propagate forward sinusoidally, and then here it's down, and everywhere in the xy plane, the E field is down, right? And then you propagate along some more, and it's back up, and it's coming down. Everywhere in that plane, it's pointing up in just a small amount. So you got to visualize all these planes moving along the z-axis, and along a plane, they all have the same value of the E field, both magnitude and direction. So that is how to visualize a plane wave. Let me tell you one more characteristic that's important. And that is right here. So you remember this guy. This is the wave number. It is literally the number of waves per radian. It's 2 pi over lambda, where lambda is the wavelength that you know and love. And I'm mean in making you use k. So now when you're talking about this three-dimensional plane wave moving along a direction, we have something else called k vector. This is the wave vector. And simply its magnitude is just k. So the wave number is just the magnitude of the wave vector, and its direction of propagation. So I'll be showing you more plane waves soon that show the k vector. The k vector just tells the plane wave where to go. So it's just an extra notation I want to tell you about, and we'll be using it quite a bit. But it's really just the same wave number you've always had, but now it has a direction.